Jayeneshwaran here, and I'm going to present the question 1, which is solving the arithmetic expression in binary. So this will be our expression that I have created: 35 base 10, 27 base 8, 108 base 16, and 101 in decimal. So for step 1, for the first question, 35 base 10, you have to convert it to binary, and you get 1, and this will be the 10011 base 2. So 27, you have to convert it to decimal first before converting it to binary. So this will be the equation. You get 16 plus 7, you get 23 base 10. You convert it to binary, you get 10111 base 2. So 1 is 16, you have to convert it to decimal 2. Same again. So you get 1 times 16 plus 8, which is the value 10. So when you total it up, you get 26 base 10, and you convert it to binary, you get 11010 base 2. And then 101 base 10, you have to convert it to binary, so 110010. So now we have all these 4 numbers in binary, which is going to help us in making it easier. So now let's look into step 2. So we're going to complete these actions first. 1 base 16 times 101 base 10. So when you convert it to binary, you get this is the numbers. But when you want to multiply in binary, it's kind of hard. So we have to convert it back. So you get 26 times 101. So you get 2626. So we are converting it to decimal for easier multiplication. So this will be the decimal numbers. This is already decimal. This one you convert it to decimal, you get 26. So you get 2626. When you convert it to binary, you get 2626. You have to divide by 2, and you get 101000100010 base 2. So now we're going into step 3, which is we got 3 numbers over here, all in binary: 35 base 10, 27 base 8, and this multiplication also we got in binary. So now we're going to do subtraction. So we're going to take 100, so which is basically 35 base 10, and minus 23 base 10, so 100. When you complete in binary, it's kind of hard. So we do it in decimal. So you get 35 minus 23, you get 12. And when you convert it to binary, you get 1100 base 2. So now we have to take this number over here, 1100 base 2. So when you add it up, you get 10 100 1110 base 2. Okay, so the final step now, we're going to convert the binary result to octal and decimal. So first, octal. So you have to group the binary number into trees. So when you group it into trees, you get like this, and when you convert it to octal, you get 5.16 base 8. So for hexadecimal, you have to group it in fours. So that's the difference. Octal, group in trees. Hexadecimal, you have to group in fours. So you get 0001, 0100, 1001, 1110 base 2. So when you convert it to a hexa, you get 149e base 16. So these are the 3 things that we got from this equation. So first of all, binary, this is the answer. Octal, this will be the answer, and hexadecimal, this will be the answer. Thank you. Okay guys, so now let's look into question 2. So real life examples of binary, hexadecimal, and octal. So for binary, we know that we use it in computing and electronics. So why do we use binary? Because binary digits represents each data. So how does it work? So if the signal which is produced, it actually will be either 1, which is on, or 0, that is off. So how it really works? Each and everything that you do in your computer, for example typing or any activities, is going to be converted into binary first, and then it will be executed as what you see in the screen. So for example, if you type the letter A, it will be 01000001 in ASCII binary. So that's how it works. Now let's look at hexadecimal. For example, where can you see hexadecimal? Hexadecimal can only be seen in color codes. So for example, even when you're using some kind of applications for like Photoshop, when you want to edit the colors and everything, you can see all those codes like hashtag FF000, hashtag 00F00. So all those codes are actually representing different colors, for example red, green, blue. So why do we use hexadecimal? Because it makes it easier for us to read rather than using block decimal. For example, if you use hashtag FF000 in binary, which is actually 1 1 1 1 1 1 0 0 0 0 0, and it's going to be very long. So that's why we use hexa. In octal, you can very rarely see these octal digits in our computer because most of us use Windows or MacBook, Mac OS, and all that. But this octal is used in Linux. So Unix file permissions in Linux, we use octal. For example, the number chmod 755 file.txt. So what does that 755 stand for? It is not just an ordinary number, but it's a octal number. Why is it octal? Because it sets the activity to read, write, and execute permissions. So the number 7 will actually read plus write plus execute, while the number 5 actually reads and execute. So that's where we use octal. So these are the sum of the basic things that we know in real life examples of binary, hexadecimal, and octal. Thank you.
Hi, ma'am. So this is Visveswaran going to continue with the question 2. So what is question 2 is about? So question 2 is about, let me give a simple introduction. Create a unique real life or logical scenario involving at least 3 to 4 conditions slash inputs can be sensors, switches, decision or rules. In a simple way, which I can explain is how we're going to combine a discrete math theory with a real life scenario. So let me give my idea, which means my group idea is digital lock magic. So digital lock magic has certain rules to open the lock. So what is that? Okay. Number one, we are given a digital lock with 4 sensors called as A, B, C, and D. The lock will open if the Y equals to 1 based on rule 3. Okay. So what are the rules? When I'm talking about rule. So let me give introduction for the rule. What is rule 1? A is active, which means A equals to 1, or B is inactive, which means B equals to 0. Boolean expression A plus B bar. What is rule 2? C is inactive, C equals to 0, or both A and D are active, which means A equals to 1, D equals to 1. What is the Boolean expression? Boolean expression equals to C bar plus A times D. And what is rule 3? Because rule 3 is important on this particular lock, which means the lock won't open if B and C are both active, which means E and C equals to 1, unless D is also active, which means 1, 1, 1. So what are the Boolean expression? B times C times D times bar, bracket, and also bar. So this is the final Boolean expression. So let me go to question 2. Boolean expression for Y. So in this particular question, a question said that we have to combine. So how I combine is, this is rule 1, and this is rule 2, and this is rule 3. So which means Y equals to bracket A plus B bar times bracket C bar plus A times D times bar bracket B times C times D bar. So in a simply expression using Boolean algebra. On this particular thing, how I'm going to simpler this formula using De Morgan's law. So what is De Morgan's law? So this is the simple explanation I given for myself to understand what is De Morgan's law and also for the presentation. Okay. So De Morgan's law is the negotiation of A and B is the same as not A or not B, which means B times C times D is equals to same with B bar plus C bar plus D. So this is the De Morgan's law. So by using De Morgan's law, I can simplify this formula is the final output is Y equals to bracket A plus B bar times bracket C bar plus A times D times bracket B bar plus C bar plus D. So these are the final output for the question 2. Okay, let me continue with question 3. Why so long? Okay. So make it simple. So we have to use this to verify that the logic works correctly by constructing a 4 variable cutoff map. So before using cutoff map, I just use the truth table. So which means I'm using 16 variables. So as you can see, A, B, C, D, B bar, C bar, A plus B bar, A times D, C bar plus A times D, B bar, C bar times D, and finally you can get Y. So this is my carrot map. Okay. So the carrot map state that, hence the carrot map confirmed that the Boolean expression Y equals to bracket A plus B bar times bracket C bar plus A times D times bracket B bar C bar D matches the logic defined by the truth table. So the truth table is the same as the Kernoff map. So how to do the truth table? And they have rules and regulation for the truth table. This means AND or OR. That is the particular rules got for AND table and particular rules for OR table. By using that, you can get the truth table. So above one is the truth table and below one is the cutoff map. So continue with the question 4. Draw a logic circuit diagram based on your simplified expression. So based on the rules, I have to explain how the expression can be changed into logic diagram. As you can see, A go to the this one and B go to the B bar. Then both plus using this diagram. So A plus B bar. So this one is A plus B bar. And this one C bar and this one A D. So A and D can be times. So the final output is C bar times with the A times D. So C bar plus A times D. So as you can see, C bar here, go here, then this is the symbol for the OR table, OR diagram. And this one symbol is the AND diagram. So C bar plus with AD. So which means A times D. So I can say that AD. And this particular thing, you can see B bar, C bar. So B bar, C bar, and D combined together, and it's times. So this is the AND table, AND diagram. So which means this one on this side, this one on this side, this one on this side. At the final thing, they all times. And at the final, you can get Y. So these are the logic circuit diagram based on your simplified expression. So for more simpler, so this is the OR diagram. Maybe it's be look like this because I'm drawing on this. And this is an diagram. Yeah, it will look something like this. Yeah. Okay. So or means we have to plus, then and means we have to times. So A plus B, C plus AD, and B, C, D. At the final expression, we can get Y, which is this one. So this is E. Then the next, I would like to continue with the final question. Okay. System explanation. First, I'll talk about the rule. Second, I talk about expression. Third, I talk about truth table kind of map. Fourth, I talk about logic circuit. Why are doing this? So this is a simple explanation. The digital log system operates using 4 sensors, as I told before, A, B, C, and D. The first condition ensures the system is flexible. The log opens if the sensor A is active or B sensor B is inactive. So on the logic circuit, this means the A should be 1 and the B should be 0. So A plus B should be, you get 1. Okay, something like this. And the second condition checks either that sensor C is inactive or both A and D are active together, allowing redundancy. The third rule condition blocks access if the both B and C are active without D being active to security safeguard. So these are things we did for the protection of the logging system, which means the third condition blocks access if the both B and C are active without D, which means the D is 1, C equals to 1, but the D equals to 0. So based on the odd table, 1 times 0, you will get 0. So rule 1 pass, rule 2 pass, but rule 3 equals to 0, which means the lock won't open. So that's why this is the scenario I given. Okay, let's say the test one, A equals to 0, B equals to 1, and C equals to 1, and D equals to 0. Okay, rule 1. From here you can understand the system correctly. So A equals to 0, B equals to 1, so that B bar equals to 0, because the bar is always opposite of the B. So A plus B bar, 0 plus 0 equals to 0. So if you get 0, it's obviously fail. So the operation 1 is fail. We put X over here. Okay. Rule 2, C equals to 1. So C bar equals to 0. So A equals to 0, D equals to 0 based on this scenario. Okay. So that C bar, which means 0 plus A times D, obviously 0 times 0 equals to 0. And the final one, 0 plus 0 equals to 0. So this also gets 0. So operation 2 also fail. Rule 3, B bar equals to 0, C bar also equals to 0, D bar equals to 0. Obviously, that's also fail. So do you think the lock will open? Obviously no, because rule 1 failed, rule 2 also failed, rule 3 also failed. So the lock won't open. The lock won't open, so what is the function of the lock? Okay, now we go to the function, how the lock works. Okay, with this scenario, A equals to 1, B equals to 0. Okay, so you mean A equals to 1. A is active, B is inactive. So B bar is active. So A plus B bar equals to 1 plus 1, 1. Okay, rule 1 pass. C bar is inactive. C is inactive. C bar is active. So A times D, which means active plus active times active equals to 1. So based on n table, 1 times 1 equals to 1. Okay. And the final one, C bar equals to plus A times D. So 1 plus 1 equals to 1. So based on the rules given and based on discrete theory, the second condition is pass. And last but not least, B bar is active, C bar also active, D bar also active. So 1, 1, okay. So B bar plus C bar plus D, 1 plus 1 plus 1, the condition 3 also pass. Pass, pass, pass. So the lock will open from like this to this. Okay. So the lock will open. So this is how the discrete math theory is combined together with discrete math theory with a real life example. So thank you so much. So bye from Visveswaran.
Hi, my name is Sannjaydass. Today I am going to present question 3a. Explain how binary coded decimal represent and process decimal number. Binary coded decimal is a method of represent each decimal digit 0 to 9 as a 4-bit binary number. So I build a table. So here it's a decimal digit to BCD 4 bits. So example 1, 1 equals to 0001, 2 0010, 3 0011, 4 0100, 5 0101, 6 will be 0110, 7 0111, 8 will be 1000, 9 will be 1001. So for example, if you want to convert 39 decimal to BCD, so 3 equals to 0011 in BCD and 9 equals to 1001. So the second one is 9541 converted to BCD. So 9111001 and 5 will be 0101, 40100 and 10001. So note that you can also convert BCD to decimal, like BCD 0010 is actually 2, 0100 equals to 4, 1000 equals to 8, 0011 equals to 3. So 3b, explain why BCD is used in some digital system instead of binary, and briefly describe one application where BCD is preferred. So the reason, human readability. BCD map directly to decimal digits make it easier for devices that display numbers like counters, clocks to process and show readable result. So BCD represent each decimal digit 0 to 9 using its own 4 bits binary code. So it's make easier to convert between binary to decimal because each digit is stored and processed individually. Devices like clocks, calculator, counters benefit from this because they display numbers directly to human. No conversation and complex logic is needed to show correct decimal digit. So the second one, avoid binary rounding error. In binary, some decimal value like 01, 02 or 03 cannot be represented exactly. So BCD avoids this by keeping decimal digit intact, which is crucial for financial or accounting system. So in pure binary representation, like floating point, certain decimal number cannot be stored exactly. For example, 01, 02, 03. So in financial and accounting or commercial system, such tiny inaccuracy can lead to significant error over time. So BCD avoids this issue by storing each digit separately. So numbers like 01, 0.1 are stored exactly as 0000 or 0001. Application where BCD is preferred. Digital clock and calculator. In digital clock, time is displayed as 12:45 and 59 seconds. Each digit 1, 2, 4, 5, 5, 9 is separate decimal. So BCD represent each digit individually in binary. Example 1 equals to 0001, 2 equals to 0010. So this approach simplify the circuit required the drive 7 segment display for each digit. Since each digit can be directly mapped to its corresponding binary representation without converting a full binary number into decimal. So the second one, calculator. Calculator where the performance arithmetic. So calculator display result is decimal and not binary. So BCD ensure that each digit is stored and processed independently and preserving accuracy and avoiding binary rounding error. With example with numbers like 0.1 or 0.2 or 0.3. So it simplified decimal based operation such as addition, subtraction, especially in low power hardware environment. Question 4. Explanation of combination and permutation and recurrence relation. So permutation is about arrangement where the orders matter. So a permutation is about arranging things in a specific order. If you care who come first, second, third, you may use permutation. So in other words, permutation is like lining up people, books, or number where the sequence is important. So for the combination is about selection where the order doesn't matter. So the combination is about choosing things, not arranging them. So you don't care about the order. The same item in a different order are considered the same group. So in other words, combination is like picking a group of friends to go on a trip. So it doesn't matter who your name first. Okay. So as a concept, I built an example, permutation and combination. So if we have three options like A, B, C, you need to pair it by 2 by 2. So it will come as AB, AC, BA, BC, CA, CB. So it count as 6 and combination AB, AC and BC. So the difference is for permutation, if you count AB and BA, it's a different thing. It's not the same thing. But if for combination, AB and BA is the same thing. So question 4A, explain the practical application of combination and permutation in real life scenario. So permutation scenario, lock combination on a safe. For example, I have a locker with 3 pins, 3 digit security code. So the possibilities is the digit will be 0 to 9. So the digit cannot be repeated. So the formula will be P bracket N R close bracket equals to N factorial over bracket N minus R close bracket factorial. So N equals to total items and R equals to item you are arranging and I equals to factorial. So factorial means multiplying whole numbers down to 1. So if I have a safe locker with 3 digit security code, so the possibilities total item will be 10 and the item you are arranging will be 3. So P 10 over 3, it will count as 720 possibilities codes that you can use to open my safe. So combination scenario, choosing ingredient for a sandwich scenario. So a customer can choose 3 topping from a list of 10 available ingredient to customize their sandwich. So the order which they select them doesn't matter. So the order is doesn't matter. So the formula we can use is n factorial over r factorial inside bracket n minus r close bracket factorial. So we have 10 available ingredients. So 10 and 3 topping. So the total combination we will get up to 120 combination. So we can use the 3 topping in 120 combination or different space. And B, explain the practical application of recurrence relation in real life scenario, saving money weekly with a pattern. So you decide to save money every week. On the first week, you save 10 ringgit, and each week after you save 5 ringgit more than the previous week. So to do it's like you decide to save the money every week, right? So it's create a pattern where the first week you will save 10 ringgit, the second week you will save 10 plus 5 ringgit, 15 ringgit, and the third week 15 plus 5, 20, and the fourth week 20 plus 5, 25 ringgit, and so on. So we define the function s and inside bracket it's represent the amount of save in a week. So base case S1 equals to 10. So you start with 10 ringgit. So S n minus 1 plus 5, it's you add money like 5 ringgit more than the previous week's saving. So why is recurrent relation? So a recurrent relation is a way of defining a sequence where each term depends on one or more previous term. In the case, each week savings depends on the previous week's amount plus a constant RM5. The future value is built based on the past. So real life application. This recurrence pattern is useful in many real life planning situations such as budgeting or saving plans like the example that I give, or loan replacement, repayment, or fitness tracking, or scheduling tasks that increase in complexity. Thank you.